Now we're going to talk about why the orbitals have the shapes they do and how we figured out what those shapes are. And I do not expect you to completely understand this or even really remember it very much, but I hope that you come away with, yeah, there's an explanation for that. There's a reason that they're those crazy shapes. I don't really thoroughly understand this. I'm not sure that anybody really does, but this is how it came about. So psi squared is the probability density. Psi is a wave function that describes an electron. We square that, we get the probability of finding an electron at a particular point in space. So if we take psi squared, that's equal to the probability per unit volume. We see that the s orbital is spherical. So how do we get that? Well, you take that equation and you put in the quantum numbers, n equals 1, L equals 0, m sub L equals 0. That describes the 1s orbital. That's going to get a shape for you. For the hydrogen atom, we can solve those equations. The s orbital is spherical. So if you look at the shape of that result, it's spherical. And we would see the probability density decreases as you move further away from the nucleus. So we can represent that as a plot that would be a lot like a multiple exposure photograph, where you take a picture of the electron and then later you take another picture and it's in a different place. Because every time you observe the electron, it becomes a particle and it's got a specific location. But then you know nothing about its velocity. It's very important for you to understand the electron is not moving around the nucleus like a moth around a flame. I know I had that picture in my mind for a long time, that the electron's just being really random and it's jumping all over the place. That's not what it is. The electron is a wave and a particle. As a wave, it occupies this volume, but as a particle, it can only be in one place. So the electron's location is spread out over the entire volume of the orbital, with it behaving as a wave. So we could look at it this way, where each dot would represent a picture taken, and we force the electron to be a point, and so that we could see that it's in this region. As we get further away, it gets kind of fuzzy here. The orbital is not a container. It's not like a hamster ball that the electron is trapped inside. It's just a region where the electron is likely to be found. Could the electron be found over here? Yeah, it could. So if we look at this, the density of the dots is proportional to the probability density, and we see that the probability density is actually highest at the nucleus. Except electrons are not found at the nucleus. They have to be some distance away from the nucleus. So this is not quite right. Something's missing. So a radial distribution function adds a little bit to this. If you've taken calculus, that might help you to understand what's going on here. This is the total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. In calculus, you talk a lot about, well, if you divide this into infinitely small pieces and all of that kind of stuff. So this gives us a better picture. So we've got the total radial probability at a given distance r. That's the probability over unit volume times the volume of the shell at r. So the unit volume is smaller as the volume of the shell is larger. And so they oppose each other. So we have psi squared being a maximum at the nucleus, decreasing with r, but the volume of a thin shell is 0 at the nucleus and increases with r. And so the result of this is that we get a distribution like this, where the probability of finding the electron at the nucleus is actually 0. As you move away from the nucleus, the probability increases sharply, hits a maximum, and then decreases again. This maximum for a hydrogen atom is at 52.9 picometers, and that corresponds exactly with the radius that Bohr predicted for an orbital in his hydrogen atom, 52.9 picometers. So they came up with the same number, but there's a very important conceptual difference. In the Bohr model, that electron, it's almost like it's on a tether, on a rope at 52.9 picometers, and it's always the same distance, and it's just going around, right? Quantum mechanics says that the electron is found at lots of different distances from the nucleus, but 52.9 picometers is the most probable. As you move away from the 52.9, the probability of finding the electron at that distance from the nucleus decreases, but it could still happen. So if we go to the 2s and the 3s orbitals, these are also spherical in shape. They're larger in size because now the electron can be farther away from the nucleus. These orbitals also contain at least one node. So here we have a nice picture of a standing wave with a string. So if you jiggle the string just right, you can set up a standing wave. And the wave is traveling down and back, and down and back. And so the string is actually moving up and down within this region. And so really, you could say that it's everywhere in this region, right? But if you took a picture of it and looked at it in one location, it would have to be here or there. It couldn't be everywhere at the same time. But when the standing wave when it's acting as a wave, it can be everywhere within that. Orbitals are essentially standing waves. It's just the shape is really different. But it's a standing wave just like this, where if you take a picture of it or you touch it with your finger, you force it to stop and be a string again. The node is where this wave is zero. So for electrons, the probability of finding an electron at that node is zero. So here's the 2s and the 2p orbitals. So there's some probability density very close to the nucleus, and then there's this white region here that's a node where you're not going to find the electron, and then it can be out here as well. So here we see there's some probability close in here, then there's a place where it goes to zero, and then higher probability out here. So if we look at this standing wave again, this would be the node. This is that bump close to the nucleus. This is the larger bump further away from the nucleus. The electron can be here or here, but it can never be right there. It's a wave. When you make it be a particle and you pinpoint its location, you force it to be in a single place. But when you're not observing it, it's actually everywhere. It's really hard to get your mind around that. It took me a couple decades. So if you don't get it right away, just don't feel too bad. But if you want to talk about it, I'd be happy to talk. So here's the 3s has two nodes. So there's a little bump there, and then a bigger bump with a node, and then more of it out here. And so you could think of this as a really funky shaped standing wave on a piece of string, right? And the wave is here and here and here, but the wave is not there. That part isn't moving at all. Does that make sense? A little tiny bit. Every principal energy has one s orbital, because no matter what n is, L can always be zero. It's going to be the lowest energy orbital in any given principal state. It's spherical. The number of nodes it has would be equal to n minus 1. So what about L equals 1? So these are called p orbitals. When L equals 1, now we have three different possibilities for the orientation, -1, 0, and +1. And so we typically represent these along a three-dimensional axis X, Y, and Z. P orbitals are two-lobed. They have a node at the nucleus. And then as you get bigger and bigger, they have more nodes. So these are the P orbitals. They kind of look like dumbbells or balloons or something. So there's a node at the nucleus, and then there's this radial distribution moving away from the nucleus. This would be along one lobe. And then you'd see this similar distribution going along the other lobe. So this looks more like a standing wave. So if you can imagine the string in its standing wave, and it's going up and down over here, and it's going up and down over here. The electron is on both sides of the nucleus as a wave, but it's not in between, because in between the string is not moving at all. And so we can have one wave function along the x-axis, and one along the y-axis, and one along the z-axis. And m sub L, -1, 0, and +1, is what gives us these three different orientations. When you get to L equals 2, now you have 5 d orbitals, because you have 5 different values that are possible for m sub L. These get more stranger, weirder. You can read that. Here's the picture. The picture's what's important. These are really weird, although they're not as weird as the next ones. These kind of look like a double p orbital. It's got 4 lobes, and so these are in different planes. This is in the YZ plane, the XY plane, the XZ plane, and then this one's in the x squared minus y squared plane. So it's cattywampus to this one. Then there's this guy. He's just very different. F orbitals, we've got 7 different possibilities for m sub L, and so we have 7 different F orbitals. These are really weird looking. Just, observe and appreciate the strangeness. I will not make you draw those. It's like some really weird balloon art. So orbitals are determined from mathematical wave functions. We can think of them as standing waves. Waves can have positive or negative values. You think about the string in the standing wave. It goes above the axis and below the axis. So one is positive, one's negative. So the sign of a wave function is called its phase. Waves, as we saw, can interact with each other. We can have constructive interference and destructive interference. That's what causes those diffraction patterns. So when the orbitals interact, the orbitals are waves. They can be in phase with the same size and reinforce each other, or they can be out of phase and kind of cancel each other out. We'll talk more about this in chapter 8. Oh, actually, it might be further on than that. We're going to talk more about this in a later chapter. We'll stick with that. That's important in bonding, especially valence bond theory. So here are the phases. So for an s orbital, it's in one phase at a time. For a p orbital, part of it's positive, one lobe is positive, and the other is negative at any given time. But they can overlap. Positive with positive reinforces, positive with negative cancels out. Negative with negative reinforces. So all those weird balloon shapes are the regions in which the electrons are found. The electrons are what take up most of the space of the atom, And we've been drawing atoms as little balls, right? And we think of atoms as being spherical, and they pretty much are. How are they spherical when we've got all these weird balloon shapes going on? If we superimpose all the balloon shapes, we get a roughly spherical atom.